A little bit of context about the challenge that we've spent the whole semester approaching. I'll go through our methods with how we're approaching the specific challenge. We'll talk about in a minute. We have a variety of different alternatives to present to you today, similar to the method team, which we've gone and evaluated based on a variety of different criteria. And we have conclusions and recommendations for our partner organization, Autodesk. So to start with a little bit of context, for those of you who aren't familiar with Autodesk, Autodesk is a very well-known software company. It's a multinational company, and they work in a variety of different industries. They work in manufacturing, architecture, and entertainment. And we're specifically focusing our work with Autodesk around additive manufacturing. Specifically, we're looking at stereolithography 3D printing, or SLA 3D printing. And essentially what this means is we use light to photo cure and allow for a phase change from a liquid resin to a solid polymer. Over here we have the Ember 3D printer here by Autodesk, and instead of talking through all of this, we wanted to be able to show you what this actually looks like. So bear with me for a moment. What we have here is a time lapse. You see the build plate lowering, and from the resin tray, you can see the UV light there, and it's essentially converting the liquid resin in this resin tray to 3D printed objects. And if you notice, you can see pretty high resolution with this particular 3D printed object. That's one of the great features with SLA printing, and specifically with this Ember printer from Autodesk, is that they actually are able to have very high resolution with their 3D prints, down to 10 microns per layer in thickness, that allows for a great quality printed product. There are technical difficulties switching from the video. Leaving the software component, some of the light component up to Autodesk, our challenge this semester was looking more at the resin in particular. And so we needed to understand what the baseline product was that we were looking at. This is Autodesk's PR48 photopolymer resin. And on the left you can see different components that make up this given resin. Each has its own function. If you start at the top, you can see the photo initiator, a very small component of the overall resin, allows for the initiation of the polymerization process. It starts the activation of that phase change, allows it to begin converting from the liquid polymer to the solid printed product. The reactive components here allow for more cross-linking, build on the strength of the product, allow for the product to build upon itself as it's created. And finally, the UV blocker, again, at the bottom, another small component of the overall resin. It's actually absolutely essential when you're looking at the resolution. You need to be able to block some external UV. You only want to be focusing in on the area that the computer software has dictated the light should show to convert, again, the liquid resin to a solid polymer. What we became aware of through some work that was done at Autodesk and some other partners is that there are some hazards associated with this specific resin. They're identified here as reproductive and aquatic toxicity, also eye and skin irritation, and then skin sensitization. And since Autodesk is a very progressive and forward-thinking company, they want to prioritize the safety of people and safety of the environment when they're designing their products. Especially with such a new and developing industry as additive manufacturing and 3D printing is, we really want to be ahead of the game and thinking about potential considerations that many other industries only focus on at the end of the process when a hazard is already identified. So here we're trying to be more upstream in our thinking. That being said, our challenge this semester was to explore and evaluate biomimetic, green chemistry, and life cycle solutions for less hazardous stereolithography resins. Our methods for this project boiled down, this is kind of a simplified slide. First, we started with biological inspiration. Where can we look in nature that will give us ideas of a pattern phase change that we could incorporate for SLA printing? So we looked at some specific biologically inspired design approaches. From these approaches, we were able to identify alternative resin materials, and we were able to then take those alternative resin materials and evaluate them based on a variety of different criteria. So our first question that we started with when we're exploring nature, how does nature inspire design in particular, particularly related to SLA printing? And we were very fortunate to be able to build on the work of others and kind of use this as a jumping off point. Marty, Justin, and Tom here identified 11 biologically inspired approaches to look at design specific to 3D printing. And just to highlight a couple of these today that we incorporated into our alternative strategies, these are the 5 that we'll be talking about in a little bit more detail. And just to clarify and give you an idea of what this actually looks like, we're talking about taking advantage of gradients or making delta do the work. This looks at concentration gradients. When you're talking about pH change, this becomes incredibly relevant for one of our later strategies. Another one that we looked into was this functionally graded materials. And so we learned in class, and we also learned when we were looking at various use cases with SLA printing, we want something that is going to take into consideration different contradictions. We want strength, we also want flexibility. And so we wanted to explore some functionally graded materials that would let us get at different use cases within some of these different alternatives. We'll get into that in a little bit. As I mentioned before, we took those biological inspirations and were able to identify alternative resin materials. And using those alternative resin materials, we used 3 different criteria to evaluate them. So we had 3 main questions. Is this alternative material feasible for SLA printing? Is it safe? And what are its potential use cases? Where can it be used out in the world? So for technical feasibility, we developed a checklist. We'll go into some of the strengths and drawbacks of each strategy as we present them, and we have a summary slide with a lot of these different parameters that we evaluate. For hazard potential, we understand that there are different routes of exposure depending on what part of the life cycle you're looking at, whether it be the very beginning, more upstream raw material sourcing, or very downstream, say the material or resin disposal or the print disposal. And so for the purpose of today, we wanted to just talk about the hazards as they relate to the more downstream end of the process, the consumer-facing process. So this includes handling the material, by material we mean resin, disposing of the resin, the print and what it's used for, and then finally the print disposal. We also realize that there are many hazard endpoints that we could go and look into, but for the purpose of today's presentation, we're going to focus on the 5 that we identified for the current PR48 resin at Autodesk to kind of narrow our focus for the presentation. That being said, as we go through, we're going to be talking about where there are data gaps in terms of hazard information, where we were able to identify hazard, and where our alternatives will potentially be able to reduce the hazard. And finally, when we looked at use cases, we wanted to see what kind of great things are going on in the world using 3D printing, what are the current use cases. We also wanted to look into the literature and see what are some exploratory or experimental use cases that maybe aren't commercially available yet. And finally, we wanted to focus on biocompatibility. Many use cases end up being included in the human body. Say you can do implants, you can do drug delivery or tissue regeneration, and so you really want to be thinking always about how safe can we make this, and is this going to be compatible for human life? That being said, we have 5 different strategies to share with you today. We've organized these strategies by level of intervention. So we'll start with replacing a single component of the existing resin. Next, we'll talk about modifying the existing resin with some changes. And finally, we have more of our breakthrough or blue sky strategies that look at completely new ways of being able to do SLA 3D printing. And all of that being said, I'm going to turn it over to Brian to talk about our first approach and our first strategy.
Okay, so our first approach and strategy was to replace the photo initiator. Our initial hazard assessment found that even though the photo initiator only makes up 0.4% of the entire resin formulation, it is also one of the more problematic ingredients in the entire formulation. For instance, we found that it's a reproductive toxic in category 2, it's also an aquatic toxin, and it can be a skin irritant. So we thought about the problematic hazards that the photo initiator TPO would have, and given our backgrounds in 3D printing, we also knew that there were other alternatives that we can use. So we thought about curcumin and riboflavin as our proposals for today. Curcumin is an extract from the turmeric root of the curcuma longa plant. Riboflavin is vitamin B2, which is a water-soluble vitamin, and it can be readily found in milk and other dairy sources. And in terms of the bio-inspired approach that informed this strategy, we used the optimal activator because essentially the photoinitiator is what's starting the reaction in the first place. So we looked into nature to try to figure out what can activate this reaction. So this slide is meant to depict how we envision curcumin and riboflavin working in conjunction. So through our literature search and research, we found that curcumin is actually a really great photosensitizer. So when it gets hit by light, it gets excited, and when it reacts with riboflavin, it'll create a radical, which will then initiate the. So it'll then initiate the reaction of the acrylate monomers. So essentially, it will work the same way as a TPO initiator. Moving on to the hazard assessment of curcumin and riboflavin, we actually split up, or we looked at the individual components. We looked at curcumin and riboflavin separately because they're essentially performing different functions. Curcumin is the photosensitizer here, and riboflavin will be the photoinitiator. And to kind of summarize what's going on the table, the red dots are meant to depict an identified hazard. The green dots are meant to depict a decreased hazard, and the clear dots are meant to depict hazards for which we don't have any available data. And as Leanne pointed out in the very beginning, we did want to look at skin sensitization, but because we can't, because skin sensitization relies on chronic data, we didn't have any available data, and we omitted it entirely from this for this resin, or for this strategy. So to compare curcumin and riboflavin to the current photoinitiator, we found that in terms of skin irritation, curcumin would be provide a decreased hazard, and in terms of reproductive toxicity, it would also provide a decreased hazard. We concluded that in terms of aquatic toxicity and eye irritation, it would still be an identified hazard. So it wouldn't necessarily be changing that from the current photoinitiator. And for riboflavin, we didn't have any data for skin irritation or eye irritation, as well as reproductive toxicity, but we did conclude that in terms of aquatic toxicity, it's a major improvement.
Brian, we're just going to adjust the brightness on this.
Oh, yeah, definitely.
Thank you. Yes, thank you, Akosh.
What a contrast.
Yeah.
Yeah, we tried it downstairs and made the grid.
Thank you, Akosh.
Sorry, I mean, we looked through these slides like all last night and all this morning, so it kind of like, I memorized everything. This is what I was talking about. This is the key we're talking about. Yeah. Sorry.
It's great.
Kind of just came into this assuming that you all knew. Just to summarize, these are the findings that we found for the hazard assessment of our alternative strategy. In terms of current use case or use case of our alternative strategy, we envision that because this is a direct substitute of the TPO photoinitiator, it wouldn't provide a drastic change to what Autodesk currently has, and the use cases would be pretty much the same, or would be exactly the same. So this is a picture we extracted from Autodesk website. So you'll still get the same. We predict that you'll still get the same resolution, the same material that you want. And moving on to our approach to strategy of modifying the acrylate-based resins, it's going to be Chen.
Thank you, Brian. So our second approach in designing a new and safer 3D printing resin is focused on modifying the acrylate-based resins. So if you recall, the acrylate-based resins makes up more than 99% of the current formulation. So any change or improvement in the hazard profile of the the resins or the monomers would be a highly effective way to attenuate the hazard of the overall formulation as well as the final product. So the first strategy under this approach involves taking advantage of the huge variety and abundance of naturally occurring triglycerides, also known as oils, found in nature. And build 3D printing resins from those monomers, from those triglycerides. And with that, we can potentially fine-tune the mechanical and physical properties of those monomers and the polymers, and hence we call that unity within diversity. So within this single approach, we can build a very diverse library of monomers and polymers. So shown on the bottom here is a proposed molecule with 3 acrylate. So that's a acrylate functionality, and that is the group that will photopolymerize and cross-link the material into a solid resin. And shown here is a molecule with 3 acrylates grafted onto a triglyceride, which is a molecule shown here. And compare that to the current formulation, the settlement SR494. You can see that they share the same acrylate functionality, but because of the increased molecular size and molecular weight, we expect the bioavailability to be decreased, and thus the hazard through skin contact or through ingestion should be also decreased. As I mentioned previously, we have a wide range of different naturally occurring fatty acids, and we can swap those side chains to an arbitrary fatty acid chain to fine-tune the mechanical and physical properties of the monomer. So if you look at this molecule, it has 1 acrylate per monomer, and comparing that to the previous slide where we have 3 acrylates per monomer, and those 2 molecules should produce 2 polymers with very different degree of cross-linking and different mechanical and physical strengths. And finally, in addition to the mechanical and physical properties, we can also use the side chains to chemically modify the polymers, either the material either in the monomers or in the polymers. So shown here, on the right-hand side, we have this acrylate, which is still used for photopolymerization, but on the left-hand side, we have this hydroxy group, which can be used to graft other polymers. And shown here is an example where we propose to graft polylactic acid, which itself is also a biorenewable and biodegradable material, to basically expand the library of molecules and explore the different interesting properties of the materials. So compared to the PR48 resin, we believe that due to the decreased bioavailability, it should pose at least a decrease in skin irritation, if not improvement in the other areas or the other criteria we evaluated. And just to mention that because the triglycerides are sourced from nature, it is biorenewable and biodegradable because those are natural substrate for bacteria as a food source. So comparing that to the current resin material, that is also a very nice feature to have, even though it's not directly geared towards the making a safer material. And in terms of potential use cases, as we mentioned, because the new material will have different mechanical and physical properties as compared to the current formulation, we envision that it can be applied to cases where long-term skin contact and a high degree of customization is required, such as in this case, a implantable or wearable hearing aid device. And with that, I'll pass it on to Brian.
Great. So our second strategy in modifying acrylate-based resins is acrylated glycokitazine, which I'll just call MGC for now. And our biological inspiration for this is chitinous materials from exoskeletons of arthropods like crab or shrimp. One fun fact about chitin is that it's the second most abundant biopolymer on Earth after cellulose. So if you find yourself at trivia night and they ask you what's the second most abundant biopolymer, your answer should be chitin. In terms of the bio-inspired approach, we really looked at self-organization because chitin does organize itself to provide the first layer of protection for arthropods. So the shell protects it from anything really penetrating inside its body. And before I move on to the next slide, I also want to point out that in terms of sourcing of chitin, you can actually break down the shells of arthropods remove the calcium, and then you can use a sodium hydroxide solvent to deacetylate the chitin into chitosan. You can also buy this from chemical manufacturers like Sigma Aldrich. This slide is, I wanted to illustrate what MGC looks like. In addition to being biodegradable, biocompatible, and relatively safe for humans, chitosan is also relatively insoluble. So the reason, so the only way you can solubilize it is by using an acidic solvent or by adding a glycol group to its backbone. So once you add the glycol group to the chitosan, it becomes soluble at pHs of greater than 7. And the main reason why you want to solubilize chitosan is so that if you want to graft the methacrylate group via by using either methacrylic anhydride or glycidyl methacrylate, you need to solubilize it. Another key point that I want to point out about MGC is that if you want to alter the degree of methacrylation, you just alter the incubation time with methacrylate and glycochitosan. That's something I want to point out about this slide. In assessing the hazard profile of methacrylate glycochitosan, one thing I want to point out is that we're really not changing. We're still using a methacrylate group, an acrylate-based resin. So in terms of aquatic toxicity, we predict that it'll stay the same because of the waste disposal and in the material handling. In terms of eye irritation and skin irritation, we predict that it will be a vast improvement from the current PR48 resin. And for reproductive toxicity, because you're using a bigger polymer, it might be that the body processes it differently, but there's really no way in quantifying that. So we decided to leave that as a gray dot. In terms of use cases, one of the main research articles that informed our MGC strategy is its use in biomedical research. So this is a picture depicting tissue scaffolds for bone regeneration or tissue regeneration. And one thing that I skipped over in the hazard profile of MGC is that in this research for biomedical uses, it's also found that the cytotoxicity of MGC in chondrocytes, which is cartilage cells, it's up to 1 mg per mil. So that's one hazard profile that we have, the cytotoxicity for chondrocyte cells. But I also don't want to make a leap and say that it's safe for other cells and other health endpoints. But that's one thing I did want to point out, that in terms of biomedical use, MGC is well established to be compatible for tissue regeneration and biomedical purposes. Moving on to approach 3, Annie, would you want to kick us off?
Thank you. So our third approach moves away from acrylate-based technologies, and we title it pH photoinitiated resins. I'll be presenting on strategy D, calcite, before I pass it on to Cole for the metapedicle complexes. So as we look to nature, we wanted to both look for materials of interest and process of interest, and we came across the oyster, which lives in intertidal zones and attaches to the rock and experiences tremendous force from the ocean water. So it's cement. This is just kind of on like a, I don't know, but it's cement where it would adhere to the rock is of interest to us for its strong adhesion qualities, and then its ability to take advantage of the gradients within the seawater to produce this and to grow this is interesting to us for additive manufacturing. So how does it work? There's a great amount of biological literature that has come to understand the oyster better. And this is an illustration I made of what would be the oyster here and the rock substrate here. And it extrudes a protein matrix, and there's calcium and carbonate, these little orange dots, in solution. And there's also a bacteria in solution that converts urea and increases the pH. Then, because the pH is increased and there's more protons in solution, the calcium, which is positively charged, wants to get away from that gradient. And the protein matrix has negatively charged amino acids on it, so it finds a happy home and precipitates out of solution onto what was a fibrous sort of gel matrix into this calcified, really strong, quote-unquote, cement. And, as we looked at this example, and, part of the bio-inspired design process we've been learning about is, what do we keep about this and what can we leave for the oyster itself. So we decided to first look at this strategy just looking at the calcium and carbonate. Here's an illustration of what we sort of depicted as the ember resin bath. Then if you were to shine light and be able to increase the pH at the same time in a localized region, it would order itself from a liquid to a solid. To go more into detail as to how we were thinking about that in 3 steps, we have the initiation. We thought we could just use the calcium carbonate as a proposed strategy. Thanks to the literature in soil remediation, uses bacteria-induced cementation, which takes the dune sand and has the calcium and carbonate bond together upon the bacteria in solution, bringing the pH up. This is a brick company that does that, so typically cement is made with a high heat limestone shale. This uses no temperature at all to get loose particles to a solid brick. Propagation is our next step. How long is this going to take? I said the oyster does it overnight, but we're trying to 3D print here, and we want it to go pretty quickly. So layer by layer, we would predict, having not done this in the lab ourselves, from a pH from 7 to 8, calcite precipitates out of solution fairly quickly, almost immediately. And then our final step, termination. This would be, where we really have our looming questions. If we're able to do some lab work, how localized can we get it to just bond to the resolution that makes SLA really competitive against other forms of manufacturing? And so, if we don't, I'm gonna take it away for a second. So if we don't want to use bacteria because it's alive, it needs nitrogen, oxygen, it goes where it wants. What technology can we use to do a localized pH gradient? And that comes from 2D lithography, which is photo-based generators. And how does this work? You shine light on what is essentially a salt. There are a lot of photo-based generators out there. I'm not going to go into the details of these chemicals today, but basically, you shine light, there's a byproduct, and it produces a base. And this base is what increases that pH. So then we began to analyze the hazard potential for this strategy, and calcite as an aqueous solution for the material resin, and then also as a solid product for its print use, would be an increased or an improved hazard profile for all 4 endpoints. It's also, calcium carbonate is a waste product from marble quarries, so depending on where you source it or where it's commercially available, another key advantage. For the photo-based generators, they are largely a research chemical. They're not in really the public sphere, so there's not a lot of data out there. In our final report, we'll go more into detail about which ones we could use over others, looking at the chemical functions through some of the help we've had through this course with Marty. We want to point out that while we haven't figured out the final concentrations, again, we haven't done this in the lab, of what these would be. The calcite would be more of the monomer, and the photo-based generator would be more of the photoinitiator. So it'd be a really small percentage, we think, and there also could be some post-processing of getting it to rinse out. So we're still hopeful that it could be an improved hazard look. And then, to not speak too quickly, I think we still have time. I'll slow down on this statue of David. And what do I want to say about this? There are many potential use cases for this. I had a whole bunch of pictures up here. One of them is really interesting. There's a company, I think it's a Chinese company, it's called CT Bone, prints bone implants. And if we could bring this to an SLA technology, they use a powder and a binder, so there's some hazard questions there. And also the mechanical properties of actually getting these ions to bind to themselves could be intriguing. And then the resolution would be really high, so you could potentially have an implant that could better integrate cell growth. But basically I bring up this, in addition to all the versions of art and architecture and prototyping and education, it would be awesome if we could print something to the resolution of Michelangelo and have it be actual solid marble. But we want to go back to this oyster example and compare both the inorganic, which is the mineral calcite, and then the organic, the protein matrix, and say, if we can pattern with pH, and we're looking out into the wide world of biological materials, what are the hard and soft composites that we could bring together to make something that's really intriguing, that's starting to address some of those design trade-offs Leanne mentioned in terms of rigidity and flexibility. So I pass that off to Cole as we get a little closer to answering that point.
Ever so much closer.
A lot closer. Cool.
So as Annie mentioned, we were looking to nature to try and find composite materials that could be functionally gradient. And this is something really exciting in nature that we cannot tap into with current SLA techniques. So being able to create something that is more rigid in some places, more flexible in others would be a huge, huge technological advancement in the field, and not just something in biocompatibility. So we looked to the mussel. The mussel is a really exciting organism. It's studied very in depth. Philip Messersmith here at Berkeley has done a lot of work to understand these systems. So how does the mussel do this? How does the mussel extrude this strong mussel-byssus thread and adhere to a substrate in the intertidal zone? So let's look at this system. So essentially what the mussel does is it excretes a protein rich in dihydroxyphenylalanine, or DOPA, this molecule here. And when it excretes it into seawater, seawater is an alkaline environment, high pH, and that deprotonates the DOPA and allows it to coordinate to a metal center and produce this strong byssus thread that adheres the mussel to the substrate. Right? So again, just as in the oyster example, we have a pH gradient that's initiating a chemical change that allows for a strong adhesive material to be produced in nature. So again, we're finding this pH gradient being a super important thing in nature that we would like to mimic. So just to reiterate, we have these, we're focusing, a lot of the compounds that we're focusing on, just to reiterate what Annie said, are these quaternary ammonium salts, and there's a wide family of potential salts that could be used. We're investigating some that we believe have the lowest hazard profiles possible, depending on the amines that are produced. But these are photolabile compounds that produce bases, localized pH gradients with light. So this is how we can take the mussel's technology and bring it to SLA. So what would this system look like? We envision that you would have these sort of protein mimetic, catechol-rich, DOPA-rich oligomers in solution with calcium carbonate ions. And with the irradiation of light, the photo-based generator would increase the pH and allow these catechols to coordinate to the calcium center. Now this is something that's observed not just in mussels, but in the cement excreted by sea worms and tube worms. So these systems are understood and are studied in the literature and produce these cross-linked matrices, these composite materials of both calcium carbonate ions and crystal lattices in conjunction with these sort of protein metal complexes. So this is a really exciting technological advancement because, and I want to emphasize, acrylates, the current SLA technology, either the monomer reacts to the bulk polymer or it doesn't. There's only one level of cure for the monomer, from the point of view of the monomer, right? If we were going to sit on it. It either reacts or it doesn't. But this system gives us 3 well-defined levels of cure dependent on the pH that we induce with light. So it would allow us to potentially produce functionally graded materials. And as I said at the beginning, this is a super exciting technological advancement in that it would allow us to produce, you can imagine the bulk properties of, say, an adhesive gel all the way up to marble or a hard shell, if you will. And being able to run the gamut in terms of mechanical properties and everything in between, and use pH and the photo-based generator, the precision of a photo-based generator to tune that functionality across a bulk piece would be a really exciting development in the field. So we're really excited about this. Metal ligand complexes, in terms of their hazard profile, they have been researched extensively for biomedical applications. They've been tested for fetus, repairing tears in fetuses and other sort of tissue tears. So in terms of these 4 endpoints, we found that metal ligand complexes are the effective monomer, which would produce most of the formula, would be a significant improvement to the hazard. As Annie mentioned, photo-based generators are something we're looking into more. They would be very low concentrations, again, posing more as the initiator of the process. But again, we're looking at quaternary ammonium salts and trying to find the safest possible options for those. So I already sort of talked about this, but what could we possibly use these sort of functionally graded materials for? I mean, we still implant metal pieces into human beings in order to produce joints. But imagine, if you will, if we could produce something that had the soft, pliable parts of cartilage that mimic cartilage, and then also the hard, rigid parts that would mimic a bone. I'm not proposing necessarily that we throw photo-based generators inside people's joints tomorrow, but I do think that this would be a huge leap forward in terms of customizable and tunable, flexible but also rigid parts. It's a really exciting potential use case. So just to reiterate our strategies today, first we were looking at replacing, just dropping in a different ingredient into the current formula. Two, we were looking at modifying the current acrylate technology and using bio-derived oligomers in order to sort of modify that system. And then lastly, we were looking at our more biologically inspired systems for new stereolithographic processes. And again, we had three basic evaluation criteria: the technical feasibility, the hazard profile, and then the potential use cases. So I'm just going to sort of summarize how we understand the technical feasibility of all of these different strategies. So just to focus on the first approach, replacing the photo initiator. Obviously, the main question is, will this initiate? So that's the main question. But everything else about that system is essentially the same. The chemistry is the same, and we expect the propagation and the termination of that polymerization to be effectively exactly the same as in the PR48. And a huge improvement is that TPO is really, really expensive. But turmeric and B2 you can buy at your grocery store. So that would be super exciting if we could get that to work, and would be a lot cheaper actually. In terms of modifying the acrylate resin, we have some questions about the mechanical properties of chitosan and triglycerides and incorporating acrylates into those systems. But we actually see those as being potential benefits. Triglycerides, as Chen mentioned, could be used for maybe soft, more wearable parts, something that doesn't need to be super rigid. And the chitosan could be used for, again, biomedical applications. So we see these questions as being sort of areas for further research. And again, the initiation, propagation, termination, still using acrylates, so the polymerizing is fundamentally the same. There's some questions of the price of chitosan, especially because we have to modify its structure in order to use it, but we're pretty confident that these would work. Then for our more kind of out there SLA ideas, we have some fundamental questions about how these systems would be initiated, whether these crystal lattices would actually nucleate, how they would nucleate. These systems aren't still super well understood, but the exciting possibilities in the mechanical properties and in the mechanical properties of these technologies is so strong that we're really excited about it. We think the resolution photoacid and photo-based generators are used to make nanoscale features in 2D lithography, so that's a boon right there. One difficult part, of course, is that these photo-based generators are not commercially available. They're largely research chemicals, would require a lot of optimization to be used in these systems. So that's something to consider in terms of the technical feasibility. But now I'm going to hand it over to Leanne to summarize the hazard profile of these strategies.
That's cool.
No problem.
Great. So we also wanted to be able to look at hazards across all of these different strategies. And I should say that looking at the key at the bottom here, we've identified certain data gaps, certain areas where we've identified even just single hazards for these given endpoints, and also where we expect there to be estimated reduced hazard. This chart put together the hazard profiles for the different strategies, some of which had multiple chemical components. So for example, what Cole just touched on, the metal ligand complexes here, use both the metal ligand complex that had less of a hazard, we expect a reduced hazard, as well as the photo-based generators, which we expect that there would be some identified hazard. For the purpose of this chart here, we were conservative in our hazard estimates. If there was any indicated or identifiable hazard, it's included here, given the chemical components that we looked at today. So looking at this by strategy, we're seeing improvements for eye irritation and reproductive toxicity for the first strategy using curcumin and riboflavin. We see still existent hazards for skin irritation and aquatic toxicity. Looking at some more of the modifying the current resin, we still see that aquatic toxicity is something that we still need to consider, but we do see improvements when it comes to skin irritation, and for the glycochitosan acrylates, we see improvement when we're looking at eye irritation. For the last two strategies, we have a lot more questions, and a lot of the reason that these are indicated as identified hazards, again, has to do with the photo-based generators. The other components that we looked at are essentially non-hazardous for many of these endpoints. And I just wanted to point out a couple things that we noticed across the board here. As we mentioned at the beginning of the presentation, skin sensitization requires more long-term and chronic studies, and for many of these components, things like curcumin, riboflavin, calcite, chitosan, they haven't been explored for long-term studies because acutely or in the short term, they tend to pose not that much of a hazard. So there hasn't been significant testing, and so we've indicated data gaps for across the board for all of these strategies. Another thing I wanted to point out is reproductive toxicity here. As you all may or may not be aware, here in California we have something called Prop 65 in terms of regulations. It's a regulatory list that lists carcinogens, so cancer-causing agents, reproductive toxins, and developmental toxins. And so if you're trying to prioritize in terms of maybe impending regulation, certain chemicals being added to this Prop 65 list, you might want to prioritize the reproductive toxicity particularly. And so we do see, based on available data, some given improvements across these strategies, even what we're seeing for the calcite resin and the metal ligand complexes. So just to summarize this across strategies, there are definitely areas where we still have identified hazards like aquatic toxicity, and we do see some decreased hazards. For aquatic toxicity in particular, we know that this is a particular concern for Autodesk. Aquatic toxicity comes up for many of the different components that I listed in the earlier slides when I went through the different components of the PR48 resin. But as Cole and Annie both mentioned, the relative components that lead to the hazard, so the photo-based generators, for example, are expected to be very small components of the overall chemical formulation. So again, that's something to consider. So that being said, there's a lot more to consider with hazard considerations, and we know that Autodesk is already currently working with Justin Boers on adapting a hazard assessment to look at all elements of the life cycle when it comes to their resin. They also are classifying the hazard level from very high to low hazard, and they want to look at evaluation confidence. So how certain are we that a particular chemical poses a hazard or not? Are we somewhat certain? Are we really certain? So Justin's been working on that, and he shared his work with us this semester. Unfortunately, due to time constraints, we don't think we'll be able to fully implement his assessment for each one of these strategies, but it'll be interesting to see how Autodesk can use our findings and incorporate their further hazard assessment using our given strategies. So to conclude, across all of these strategies today, we talked about the ones that Brian and Chen introduced, more of the incremental changes, and then our breakthrough strategies there at the end. They're the more out of the box, the more blue sky would require changing the technology more significantly. We're suggesting that if there's going to be focus on more current or recent implementation, that this is going to happen with more of these incremental strategies here. As there's more information understood about the hazard, they might be more tunable. They also provide a wide array of different use cases to prioritize. The breakthrough strategies is kind of what we see as maybe a potential for the future of 3D printing, maybe the future of SLA. We wanted to make sure to include that as a different way of looking at this challenge that Autodesk brought to our attention that we worked on this semester. And that being said, we would once again like to acknowledge our professors. Thank you guys so much for all of the time and effort you put in to help us molding this project this semester. And again, Autodesk and their partners, Dawn and Brian, thank you so much for all of your input on this project and for the opportunity to collaborate. So, thank you.
Questions for the Autodesk team?
Are we doing the calling? Are you doing
Thanks. I really liked the presentation. It was awesome. And particularly fascinated by the metal catechylate mode of polymerizing and solidifying the material. And so you're suggesting that by adding, by increasing the level of coordination of each metal ion, you might make it stronger. So I'm curious whether you think the calcium catechylate bonds are as strong as the iron catechylate bonds?
They're not.
Not. Okay, so then leading question. So then maybe another way of making a functionally graded material is to add different levels of trace metals. Like you can have calcium, or you can have a little bit of aluminum, which is 3+ and coordinates much stronger. Something like that. I wonder if you've explored that, or if it sounds like anything interesting to you.
I think our motivation for the calcium was coming from our hazard perspective, but coming from the mechanical properties, the chemistry of all of these things could be explored more, and I think that's another reason why we're intrigued by this strategy, is because it has sort of these swappable, and largely we're suggesting a wider library of looking at this sort of pH gradient. So yeah, it's really open to suggestions.
Two questions. One is, have you, in the literature, have there been examples where people can control that pH gradient fairly precisely or not in other applications? That was one question.
Yeah, I mean, in two-dimensional lithography, like photo-based and photoacid generators are used very precisely, and they can have pKa value, like their conjugate acid can have really high pKa values, and they can have really high quantum efficiencies. I don't know if we have any. There isn't really significant data to show exactly, like a curve we showed in our slide, how that happens. But these are well understood systems and are very precise. And because of the way that stereolithography works layer by layer, it's actually sort of just, if you can think about it, as just adding all those two-dimensional steps up into a three-dimensional system. We are confident that it would work.
And this is more a production question, or actually more an implementation question. To what extent did Autodesk share with you who their suppliers are? Because in some ways, Autodesk doesn't do chemicals, they buy chemicals. And I'm curious to what extent they were interested in some of these as potential product that they could offer Autodesk and others in the future. And maybe Autodesk should answer that question.
Brian, you feel comfortable?
I don't know how much conversation there was. We provided them some connections with the industries that supply the SDS and some of the other information I have available. I don't remember to what extent that communication existed. They're fairly proprietary about everything they do, so getting the SDSs for the students was a bit of a challenge.
So with the pH balanced ones, it seems that the big hazards there were the photochemicals that were changing pH. Do you consider other ways to do that? Because I know that the Ember is photo-based, so it would be nice to not have to change all the hardware. But lots of other 3D printers work in different ways. So like there are a lot of nozzle-based systems where if you just put an electric charge on the nozzle, maybe that would be effectively changing the pH electrically with no need for that toxic photo-based chemical. Did you guys think about possibilities for that?
Yeah, I think we actually, through my first day misunderstanding of what SLA was, looked at it from more of the other approaches. Calcium carbonate has been printed through fused deposition and powder-based. I haven't done a hazard assessment of their binder that they use, but really we'd be looking at the strengths of high resolution. But clearly, there's questions we would still have coming from a bath to, working within this hardware.
Yeah, I think that within this scope of work and this project, one of our constraints was looking at the SLA technology specifically. And so luckily we have Annie on our team who's familiar with other material science and building science things, and she was able to fill in some of these other gaps. I mean, I learned a lot from it. But I think for the purpose of what we wanted to propose, the light was a key element for what we focused on this semester.
And one comment to that too is using those other methods, there's some shrinkage because some of them you have to post-process and then heat. So again, since we haven't done this in the lab, it's hard to say it would be comparably better, but it would be a parameter we would consider, especially if you're looking at precision for biomedical. You'd want it to, what you put in the software to come out, you know, as you would expect it to.
I had another question on the catechol complexes. It's a super cool idea, and it seems like it could be like really useful. But I had a question on its stability to oxidation. Most of those are deprotonated, they tend to oxidize to the quinones. They can have a very different chemistry. So how would that affect, I mean, is it a concern that that might affect the mechanical properties over time and the health aspects over time? Or is there a way to formulate it with something else that would slow that rate of oxidation?
That's a really great point. Yeah, we hadn't thought too much about that, but I mean these have actually been Messersmith here at Berkeley has like photo cured systems using these catechol complexes, and I don't think oxidation was a huge problem in those systems. But it's a really great point and something that we could definitely look into. Maybe having some sort of something in formula to like inhibit. You know,
like hydrogen bond.
Yeah, something like that. That's a really great point. But in the systems that we've looked at that in the literature, you know, that have been done, oxidation wasn't an issue, but something to think about. That's awesome.
So I guess just to add to that, I think once the complexes are formed, it should be much less sensitive to oxidation, right? Because now the electron density is shifted onto the metal ions as opposed to all localized on the calipers.
Yeah, and even like maybe acidifying it too.
Right, so I guess that would be more of a concern for the liquid formulation, but I mean just as current resin that has a limited shelf life, so will be I'm not arguing because they have a limited shelf life, that's a benchmark we should be comparing us to. Let's just acknowledge that there will always be limitations. So.
I mean, isn't the benefit if we built a system that'll glue anything to anything, right? So, as long as it's gluing things together, who cares?
So I have a question for you guys. So, you know, this is kind of related to I think there's both the triglycerides and the chitin kind of inspired things. But did you guys find any meaningful difference in the hazard profiles between acrylates and methacrylates?
So in terms of the literature on methacrylates and acrylates, there is a spectrum of hazard. I know for methacrylates, it might be a lower hazard profile than an actual acrylate. But yeah, that's as much as I can speak to that question. I don't know if you want to elaborate, John.
Oh, I think they're mostly comparable depending on the other part of the molecule.
Mm-hmm.
So depending on what is on the other side of the acrylate. So I mean, acrylate can be modified as we propose by changing the other side of the oxygen. So basically, acrylate is an ester, so we can change the other part of the ester to modulate the chemical properties. Yeah, but just in terms of if you just think of a acrylic acid versus methacrylic acid, I would say it will be comparable.
Although there's been some work done on, for biomedical resins on acrylate, methacrylate, and vinyl, the same backbone polymer. And vinyl is usually the most problematic, followed by acrylate, followed by methacrylate. If you have the same backbone. And that's based on a limited number of studies, basically 2 that I'm aware of, done cytotoxicity within biomedical engineering applications. So that's the trend, general trend.
Yeah.
And it's basically matched with reactivity of the residual.
Yeah,
right? So it's not so surprising. It's the radical is unstable is more harmful.
Right.
But it seems like your guys' strategies are more about sort of, keeping it from
Right, so we are
getting
more,
into the point where it can go do.
exactly. So we are more thinking about like a drop-in swap, or something that requires just a little bit optimization. But the mechanism of the cross-linking will be the same, but hopefully the molecule is too big to enter the skin barrier or
Right.
be absorbed and to enter the system, so that it poses a lower threat to human health as well as other organisms.
In terms of the hazard potential, I know you mentioned focusing more on the downstream, but I'm curious about whether there were other criteria that you thought about. And I realize these are maybe more during the printing phase, but respiratory or some kind of volatilization during the actual printing phase and any exposures. Especially, I guess, I think if everyone's going to have a 3D printer in their home, someday you might want to be thinking about that. So curious if you ever explored or considered that.
Yeah. Oh, go ahead, Brian.
So you're talking about during the printing process, if there's any volatilization of the resin, right? Like creating like some kind of VOC. So I know from some studies I've read that the amount of VOCs that are produced are, I would say, negligible in terms of like MRL, minimum risk level. But I don't know if you want to.
Yeah, I would say that in terms of like respiratory irritation or sensitization, you're mostly going to focus on that endpoint when you're manufacturing and working with that in more of an industrial setting. And so that's the difference between, are there going to be controls, other engineering controls in an occupational setting, like PPE, for example, that can help limit when you're, doing a lot of 3D printing all at once versus, having it in your home. There are a lot of things to consider there, and I think that for the purpose of what we're talking about today, we're lumping it in the more upstream section, but that's definitely a component we're going to talk about in our final report. And again, we're only touching on 5 things today, just because there's a lot to summarize. But our final report is going to look across all of the relevant health endpoints. So we'll have a lot more to say. Yeah.
It's certainly an area that we look at Autodesk, but most of these kinds of technologies, certainly the Ember, is not intended for home use. And so, as she said, we're generally talking about safety inside a manufacturing context. Still human health is still a factor there. It's just a little bit of a different context.
I just had a basic question, actually, going back to the actual underlying chemistry, which is the hazard of the current formulation, especially of the oligomer and the monomer, is that in their raw form? And does that, the hazards that you identified, are they ameliorated in some way when it actually gets cross-linked in the final product? Or is the concern also, does that hazard carry over once the thing is cross-linked and solid and available to be used? Is that, or is it up?
Yeah, that's a great point. And so for what we're doing today, there were the four elements at the end of the process that we're focusing on today. We lumped them together. How you would do a real hazard assessment and how Justin is considering these things is you take each one individually. And that kind of gets at the roots of exposure a little bit more clearly. So, the printed product, your exposure to touching the printed product is different than if you're going to directly pour the resin on your hand, which you wouldn't because you would wear gloves and all these other things anyway. But absolutely the roots of exposure get at the hazard, depending on if you're looking at the resin in particular or the 3D printed product. So,
it's the uninsured monomers that have the hazard.
Okay, that's not the cured.
right. So the hazard's presented initially for the resin.
Okay,
But the solid product still has a significant percentage of uncured monomer.
Okay, that's
So that's where the
And there's also a waste of concern because in trying to sort of rinse the uninsured monomer from the final printed product, you're creating a hazardous waste.
And as Chen mentioned, we're getting at some of the hazards just by increasing molecular weight. So by increasing the molecular weight, when you have that printed product, you're decreasing the bioavailability for when you're touching it with your skin, looking at the product.
There's a lot of really fascinating stuff. I was wondering with the curcumin, I didn't quite follow what mechanism it reacted by, but I was wondering, do you know are the final products colored or not? Because that's actually one of the key important features of the TPO is it bleaches and it's no longer conjugated. So the parts appear kind of clear and white when they're done instead of yellow.
I think it's fair to assume that it would be a little bit yellow. You've all cooked with turmeric. You know what happens when you add it to anything. It's going to make it more yellow. Yeah.
There's
So
no market for curry colored.
One yellow resin.
Just not in dental.
Yeah.
You have to change the aesthetic. It's not a question of functionality. It's just how do you react
Any
to
color
it.
you want as long as it's yellow. And then I was also wondering with some of the systems, did you factor in the amount of shrinkage? Because that's kind of a continually recurring problem in every single additive manufacturing process.
Yeah, so I think, because we've been talking with Chris Venter, and he did the Cadison, I guess, could have Brian jump in here, but it's some shrinkage. But there could be room for, I'll just let you explain.
Yeah, so when we talked to Chris, and he's been kind of spearheading the work with Cadison, and one of the main feedbacks he gave us about Cadison is that when you use it with the TPO photo initiator, there is some shrinkage, but there might be some potential for using some kind of wood filler or something to decrease that shrinkage. So that is something that I forgot to mention, that there might be some shrinkage, and that might affect the mechanical properties of the MGC strategy.
I think that we talked about it a lot more for the incremental strategies, and I don't think we were able to really get at that for more of the breakthrough strategies, just because for all of the strategies there obviously needs to be rigorous testing and experimentation done. So I know we did talk about it for incremental, and we can include that in our final report, but I don't know how much we can actually comment on that for strategies D&E.
Yeah, but it would be an advantage if strategies D&E did work in SLA, because that definitely occurs in the other, going back to the other question, the other forms of manufacturing those things, there's significant shrinkage in the post-processing. So if it could, it would be great.
I have a question here. So one of the comments is pretty soon every household will have one of these 3D printers. Have you thought about the disposal? I mean, what do you do? Just toss it, and whether the chemistry you're looking into plays into how you're going to dispose of the 3D print.
Right, so in terms of hazard, and Don and Brian, feel free to jump in here. So in terms of hazard for the resin itself, right now I believe it's considered a hazardous material as the resin itself when you're disposing of it.
It depends. Outside of California, you can just put it in the trash.
Right, here in California, yeah, exactly. It's kind of one of those things you don't want to be dumping down the drain. And for here in California, yeah, there are stricter regulations for what you can do with it. In terms of the print, disposal's a little bit different. I haven't heard of anything other than throwing out the print when you're done with it.
Yeah.
So one of the current best practices that is sort of I found out about through another 3D printing like SLA company is you take the parts and the unused resin and all that stuff and you put it in a Ziploc bag and you leave it outside.
You leave it in the
let
sun.
the sun cure it, and then you throw away the cured solid waste, which is much less hazardous than the resin itself. But it's just sort of funny because there's it's like these guys sold like millions of dollars of printers, and then like they're like, everybody on their forums are like, what do we do with this stuff? Like now with a Ziploc bag and throw it in the backyard. That's the state of the art right now.
So my assumption is you are not really concerned about the biodegradability of the polymers we're using. It probably is not relevant at this time.
Yeah, we definitely talked about it, but in terms of the scope of work, I think we focused on more of the hazard itself. And I forgot to mention it here, but I did add this little end piece here at the last minute, in that that's something that we had talked about previously. We're not able to comment on it today, and perhaps with the information we've gathered, we'll be able to include some of that in our final report. But it is a consideration, and it is one of Autodesk considerations when looking at this material.
Yeah, I think it's also fair to say that end of life or energy use or toxicity hazard, all these things are you can speak to this maybe, are relatively new conversations in additive manufacturing writ large. It's like the industry as a whole isn't really being pushed hard to look at really any sustainability considerations. So we're kind of diving in to these different segments, and Jared here focuses a lot on energy use. We're looking at chemistry. Often disposability of the final part is something that people tend to talk about a lot. They're like, oh, people can kind of see that waste issue, but it definitely has not been tackled head on by the industry as a whole yet. So it is important.
Yeah, well, and if it relieves your worry a bit, the end of life for most of the printers that I've measured, so I've done some life cycle assessments of about 8 or maybe 9 different kinds of 3D printers at this point. And yeah, as Don was saying, this is very new stuff, like no one else had done this before, a couple of years ago. And so not very many people are looking at it, but almost all the printers that I looked at, it was really the energy use during the life of the printer that caused the biggest environmental impacts, more so than the toxic waste of the materials that they were using. But again, it depends on the printer and its situation with utilization and all that stuff.
And at the current time, I think the waste is probably pretty low because we charge about $100 a liter for resin. Some of our competitors run up to about $1,000 a kilogram. So I don't think too many people are disposing of that unless they absolutely have to.
And I think this is a good opportunity also to mention that not only is no one thinking about the end of life for these products, but very few people are even innovating in the materials at all. So we feel very lucky that Autodesk is thinking about stereolithographic materials, period, because no innovation has happened in these materials for 30 years since they were invented in the 80s. So we think it's exciting that we're even able to innovate at all.
And to bring it back to some of our strategies, like the chitin example, it's been done in fused deposition printing, and there's still things to work out with that in terms of shrinkage and the mechanical properties. It's pretty brittle, but it can be recycled because it's basically chitin and vinegar and water, and so you can then do that in the reverse and break that down. So we think the way that we framed sort of the level of intervention could then sort of be thought of in reverse in terms of recyclability.
No, I think you made a good point because not too many people are innovating on the material. So whatever you're innovating on the material would generate interest across industry. So it becomes of interest to us to see what you're doing in a 3D printing to see how we can apply to other industries.
And I think I can speak for all of us in that I wish we had more time to elaborate on this further, to work with Justin more, to work with you guys beyond a single semester, and I wish that we had more time to be able to go through all these different great points that all of you have brought up today. We'll see where this goes.
Well, I should probably just add to that then. I mean, I think we are thrilled with what you guys have done. We wish while we would wish that you would have more time to go further with it, I think, I can probably speak for all of us that the amount that you've done and the time you have had has really been tremendous. It's been a total pleasure working with you, but then also seeing what you put together here. So I'm the least, I know the least about chemistry of anybody on this group, so I can't speak to the details, but it's really a pleasure. Working with you, looking forward to having you come and talk to our colleagues tomorrow.
Yeah.
Cool.
Yeah. On that note, we should wrap up. I want to congratulate the students. I want to thank our partners, acknowledge the teaching team, and also our source of some grant funding from the EPA Pollution Prevention Program. And stay tuned because we'll have another class next year.
Cool.